Hello everyone, my name is Marcos Arana. I'm a process engineer for Yaskawa Motoman, and today I'm here to talk about the application of our vision product called MotoSight2D Global Edition. The two most common applications of vision guidance in industrial robots are fixed camera and mobile camera setup. Before we go any further, the materials I used in today's video are DX200MH24 robot with the latest software version as of February 2016, version 1.94. Yaskawa private label camera MS300, which corresponds to Cognex model 7402. MotoSight2D Global Edition version 5.2.0. Insight Explorer version 4.9.3. And to better illustrate the application, I'm going to use MotoSim EG VRC 2015 Service Pack 2. Let's introduce a few key terms that I'm going to use freely throughout this video. Work distance. Distance between the lens to the target object. Focal length. Distance between the center of a lens and its focus point. It's a measure of the lens light bending power. Lower numbers mean the light is bent more sharply. Field of view. Area of inspection captured by the camera's imaging sensor. Fixed camera. When the camera is mounted to the fixed post or inspections happen in the same position. Mobile camera. When the camera is mounted to the flange of the manipulator arm and of arm tool. Relative job is a robot job where all the points are stored in a Cartesian system and are based on a predefined frame. Robot Tool Center Point, or TCP, is the point in relation to which all robot position is defined. Workpiece, target object. Now, let's get started with fixed camera calibration. Please note that this step is required even if you have a mobile camera setup. The first thing we need is to create what I'm going to call a pointer TCP. The pointer TCP should be somewhere in your end of arm tool, so you can physically see where the robot controller is calculating the manipulator position. We will use pointer TCP to teach the user frame to coincide with the calibrated camera frame. Please note that when setting up a fixed camera, the calibration grid should be at the correct work distance, which means that the calibration grid should be at the same height as the workpiece feature you're training in your vision job. In our case, I'm training the Cognex camera to find the Yaskawa logo on top of my workpiece, so the grid calibration should be propped up to the same height as the Yaskawa logo. Bring the pointer TCP to the calibration grid and teach user frame 2, for instance. Be sure to teach the origin of your user frame exactly where the camera defines its origin, where the x-axis meets the y-axis. Once user frame 2 is created, then move the robot out of the field of view and calibrate the camera in Insight Explorer. Make sure that the grid spacing in Insight Explorer matches the grid calibration used to teach user frame 2. If you are setting up a mobile camera, you will need to continue with me to the next step. Otherwise, you can skip ahead to teach camera vision job. Recapping, so far we calibrated our camera with the vision calibration grid. And we also created a robot user frame on the same grid. This lets the robot understand the camera data. So if the camera finds a pattern at x equals 10 and y equals negative 35 millimeters and rotation negative 15 degrees, the robot knows the origin of the camera data and which direction are the x and y axis. But user frame 2 only matches the calibrated frame where the camera was calibrated. Now, when the camera is mounted to the end of arm tool, we need to go a step further and create a user frame that moves around with the camera. This special frame is a TCP. Since it's hard to measure the point in space where the camera TCP should be, we created a robot job that calculates the camera TCP position. This job is called tool job. There are 3 arguments in this job. Local byte 0 selects which tool number you would like to write the calculated camera TCP. Let's say we want the camera TCP on tool number 2. Local byte 1 defines which user frame number we created on the calibration grid. In our case, we set this to 2 to agree with user frame number 2. The last argument is to teach the manipulator inspection position with the same tool number as we are creating for the camera TCP, which is number 2. Once we execute tool job, tool number 2 is created exactly at the origin of user frame number 2 with the same x and y axis direction. Now we can see that when we move the camera to a different position, the camera TCP represents the origin of the camera frame. And any data passed to the robot can be converted from tool frame 2 to robot base frame. So any patterns found by the camera can be related to each other even if the camera has changed positions. We are done with calibration. Now we will simply add a location tool on Insight Explorer. Let's select PatMax pattern. Teach the model region and size the search window appropriately. Be sure to change the tool parameters to suit your process. In our case, let's change the tool name to Yaskawa pattern. Set threshold to 65 and open the angle range to plus or minus 90 degrees. Since we are happy with the vision tool results, we save and set the camera to online. Now, let's bring the data from the vision tool programmed in Insight Explorer to the DX200. We are going to use the MotoSight2D Teach Bandit application for that. Go to Associate Variables and you will see all tools created in Insight Explorer on the left column. The middle column displays the controller variables available for assignment. On the left, you can see previous assignments. Let's assign Yaskawa pattern location to P5 and Yaskawa pattern pass to B5. It's important to note that the user frame number box and camera TCP number box. If you have a fixed camera, the number in the user frame box is the only thing you need. However, if you have a mobile camera, the camera TCP is the most important argument. and it's recommended to set the user frame box to the number of the user frame we created for the grid calibration. If an undefined user frame number is selected, the P variable that uses it becomes invalid. All assignments are done. Please save, then return to the main menu. At this point, you can close the Teach Panel application. There are many other things you can do here, but we're sticking to the basics for now. Almost every piece of this puzzle is in place. Camera and robot are calibrated, vision job is created, and the data from the Cognex camera is assigned to robot variables. All we're missing is a robot job to use the available data. In simple terms, we need a robot job to move the manipulator arm to the inspection position, trigger a new camera inspection, read the results from the camera and apply the data, call a process job that tracks the workpiece. Now, let's create the job that does everything we just talked about. Move J 100%, PL0. Moves the robot to the inspection position with feedback position confirmation. Inspect macro. Handles the camera inspection. Camera number. Selects which camera to trigger, 1 through 4. Number of retries. Sets how many times to re-trigger the camera if the inspection failed. Retry delay. Time in milliseconds between retries. Disable alarm. 0 sets user alarm on failed inspections. 1 disable user alarm on failed inspections. Adjust macro. Reads the camera results and calculates a new user frame to coincide with the found pattern. Vision results, P. Location of vision results written by MotoSight2D application. Camera TCP number. Tool number of calculated camera TCP. Fixed or mobile camera. 0 equals fixed. 1 equals mobile. User frame to create. Defines user frame number to be calculated based on the vision results. Vision result base frame. Origin of the user frame created by this macro with respect to base frame. Pause. Pauses job right after the creation of the user frame, giving us a chance to convert the process job to relative job. Call process job. This job contains all positions that will track the workpiece based on the vision results. The process job is converted to relative based on the user frame created by the adjust macro. Since we created the user frame based on the vision results and converted the process job to relative job, we can go back to the adjust macro and set the pause flag back to 0. Now, each time we run our vision job, the robot will move to the inspection position, trigger the camera, read the data and create another user frame relative to the vision results and affect the process job. Because all the points inside the process job are based on the user frame created by the adjust macro, and all positions are a constant relative to the workpiece. Thanks for watching this video on the application of MotoSight2D. And if you have any questions, please contact our 24-hour customer support line at 937-847-3200.